All right, we are on slide 33 of the Equilibrium PowerPoint, chapter 15. We're introducing a concept that's known as LeChâtelier's principle. Essentially, it's a statement that addresses what happens to a reaction if it's already reached equilibrium, which if it's reached equilibrium, that means the amount of reactants and products have reached their ideal ratio to be thermodynamically stable. So it's at that ratio, and then something happens that throws off the balance. Okay? When that happens, the system or the reaction that's going on in the container will shift its equilibrium to counteract the effect of whatever the disturbance was. So if we cause a disturbance, the reaction will shift to get back to equilibrium as quickly as it can and restore that ideal ratio of products to reactants that it wants to have. Okay? Now, kind of the way I think about this a lot of times, I think of it as one of the old-time balances where if you put weights that are equal on both sides of the balance, then both pans of the balance stay level. If one side has too much weight, it falls down to that side. So if I have too much on this side goes down. The side that's lighter goes up. So that at that point, it's no longer balanced. In order to get it back to balance, I have to take some of the material from this side, move it over to the other side, and then it restores the balance. Okay? So I think about LeChâtelier's principle in kind of a similar fashion, where my reaction is balanced between reactants and products. That doesn't mean there are equal amounts of both. It means it has the desired ratio of reactants to products. It has the right ratio to be stable, so it's going to stay at that balance point forever unless something happens that messes it up. So one thing that could happen is, what if we open up the container and we dump in some more reactants? So suddenly, by adding more reactants, we have changed the ratio of the products to the reactants. The reaction doesn't like it, so what happens is our balance gets shifted. There's too much on the reactant side, which is the left side of the reaction, so that side is too heavy. There's too much stuff there. So in order to get it back to balance, I have to shift some of the reactant molecules have to be converted into products. If we convert it into products, then that's another way of saying the reaction is going to proceed to the right. We're going to form more products as a result of the change that we caused. Okay? Now, so that just shows, take some reactants, turn them into products, and that gets me back to my balance point. Equilibrium is reestablished. Now, I will say the amount of the reactants and products in this new equilibrium are different from what I had started with originally, because I now have more stuff in there. So the amount of the reactants, the amount of products are both going to be different values, but the ratio will be the same. So this picture on this slide kind of shows a summary of all the different things we're going to talk about. But to change the balance of a reaction equilibrium, there are several things we can do. We can add or take away one of the reactants or one of the products. That's what the first line up there is for. If we are dealing with gases, we can either change the pressure or adjust the size of the container. If we change the volume, that will change the pressure also because they're connected to each other. Or we can adjust the temperature of the container. Each of those things can affect the equilibrium, and we're going to address each of them one at a time. This slide kind of summarizes a lot of the information, but I want to look at it on further slides. So I have a reaction. Equilibrium is nitrogen plus hydrogen yields ammonia. We've studied this reaction before. So we assume that when we're doing LeChâtelier's principle, we already have a reaction equilibrium. That's key. Okay, it's already reached the balance that it wants. But if we add a reaction component, what happens is whatever we've added, there's too much of that now. So the reaction is going to shift to get rid of it. Okay, now an example, I can add, if I have a container where this reaction is going on, I could open up, dump in some nitrogen. If I have too much nitrogen, the reaction is going to have to shift to the right to get rid of some of it. Or I could add some hydrogen. Okay? Well, hydrogen is also a reactant, So adding hydrogen, again, if I add anything that's on the left side of the reaction, it's going to cause the reaction to go to the right. But I could also add some ammonia. If I open up a container at equilibrium, dump in some ammonia, and then close the lid, now I have too much on the product side, and that'll make the reaction shift back towards the reactants. Okay? So essentially the lesson there is anytime you add something to the reaction, it's going to push it to the other side. If I add something that's on the right, it'll push it left. If I add something that's on the left, it's going to push it to the right. Okay? Now, I also, in some cases, I can go into a reaction container and remove a component of the reaction. Well, if I remove something, that's going to create a lack of that material, whether it's a reactant or a product. If I don't have enough of something, then the reaction is going to have to shift to fill that hole. Okay? Removing something creates a hole, and the reaction is going to try to fill it. So if I open up the container and remove nitrogen, suddenly there's something on the left side that I've taken away. The reaction is going to shift to the left to replace what I took. If I open up the container and remove ammonia, now there's not enough on the right side because I took it away, it's not in the container anymore. At that point, the reaction will have to shift to the right to replace the ammonia that I took out. Okay? So that's the relationship that we need to understand. Now, this graph kind of shows it all, what happens to all three components if I change one of them. So we already said, like in this graph, the first section where they're all flat lines, those are the concentrations or the pressures, actually pressures of hydrogen, ammonia, and nitrogen in the container when it's reached equilibrium. It would stay like that forever unless I did something to change it. Okay, so in this graph, what I did to change it, right at this point, and this is time right here, at whatever time this is, I added some hydrogen. So suddenly, after I added hydrogen, the amount of hydrogen spiked up to represent the amount that I've added. Okay? Now we've already said if I add hydrogen, it's going to shift the equilibrium to the right. Well, when it shifts equilibrium to the right, that's going to affect the concentrations of everything in the container. So hydrogen is the one that I'm artificially controlling. I added some hydrogen, so when it jumps up, now it's not at equilibrium anymore. The reaction is going to shift to the right to get rid of it, so I'm going to notice the hydrogen concentration starts to come down. When it shifts to the right, though, that's also going to decrease nitrogen. So I notice that nitrogen's pressure or concentration goes down. And then as I shift to the right, I'm going to make more ammonia, so the pressure of ammonia is going to go up. So all three components get changed because I messed with one of them. I controlled hydrogen, and then it affected all three. Now, this middle part right here, so the first part was at equilibrium. Right here is the point where I disturbed the equilibrium. So I see some changing that occurs. This one goes down, that one goes up, this one comes down. And I notice that after some point in time, I get back to where my lines are level again. At that point, I'd say right about here, that's where I've gotten back to equilibrium again. Notice that the amount of each thing is not exactly the same as what it was before, but the ratios are the same. If I actually set up the equilibrium expression and plugged in, like on top would be ammonia pressure squared on top, whatever that value is on the pressure, that would be on top. The hydrogen and the nitrogen would be on the bottom. The hydrogen would be cubed. If I did all the math with the equilibrium expression, I would find that this ratio of products to reactants is the same as this ratio was. It was at equilibrium before. It gets back to equilibrium at the end. It's just in the middle, there's that adjustment period where it's trying to fix the problem. So, just for practice, with this equilibrium, which way will the equilibrium shift if I remove hydrogen? If I look up there, if I remove hydrogen, it's on the left side of the equation. If I remove it, the reaction has to shift to the left to replace what we took away. So removing hydrogen will cause it to shift to the left. What about if I add ammonia? Ammonia's on the right. If I add something on the right, now I have too much of it, it's going to shift it to the left also. And then finally, if I add nitrogen, nitrogen's on the left. If I add something on the left, it's going to shift it to the right. All right, so when we're dealing with gases, we may be looking at pressure values, okay? So we can adjust the pressure in a couple of ways. We can add more of samples and get higher pressures, but we can also adjust the volume of the container. If we take a container and we shrink it down, like picture a balloon where the volume is flexible. If we shrink the volume down of the container, that's going to cause the pressure to increase, because pressure is based on the number of collisions, and in a smaller container, the molecules are going to collide more with more collisions with the same force, but it's going to give it a greater total pressure. Okay? So, this only applies to gases. If I increase the volume of the container, so take a container and suddenly make it bigger, the molecules have more space, there are going to be fewer collisions going on, the equilibrium will actually shift toward the side of the equation that has more moles of gas. So if I look at my balanced equation, whichever side, if you count up all the moles of gas on the left and all the moles of gas on the right, whichever side has more moles, it'll shift toward that side if you have plenty of room. Okay? So in this equilibrium, my reaction is 2A yields B. Both are gaseous molecules. So if I increase the size of the container, which is what I did over here, the reaction will shift toward the side where there's more moles. Well, on the left side, there's 2 moles of gas. On the right side, there's only 1 mole of gas. So if I increase the size of the container, it's going to shift toward the side that has 2 moles of gas, which is to the left. So what I notice is A are the red circles. When I shift that way, the fraction of the molecules that are red is going to increase. B is the gold circles. When I shift toward the left, the number of gold circles is going to decrease. All right, now I can do the opposite. What if I take the original container and I shrink it down? Now if I shrink it, there's less room, the pressure readings go up. What happens to my equilibrium? Well, if there's not enough room, it's going to shift, the reaction will shift toward the side that has fewer moles of gas, which is toward the right. So when I shift into a smaller container, I'm going to have more gold circles and fewer red circles. Now, there are occasionally cases where they'll ask you, what happens if you add like a noble gas to the container? Well, if you remember Dalton's law of partial pressures, if I have a mixture of gases, each gas contributes a certain amount of pressure, but the pressure of each gas, they're all independent of each other. If I want the total pressure, I would just add all the partial pressures together. Okay? So, if I have a container where like this reaction is going on between A and B, if I add a noble gas like neon, it's not part of the reaction. It's not going to do anything other than it creates some more pressure than what was in there already, but it doesn't affect the partial pressure of either of the two gases. It doesn't affect A or B. When gaseous molecules are floating around doing their own thing, they don't really care if there are other molecules in there if they don't react. Okay? So adding an inert gas like neon or argon or something like that will not cause a shift in equilibrium. It just increases the total pressure but has no effect on equilibrium. Now, temperature. Again, when we write an equilibrium reaction, we have the reactants on the left and the products on the right, but really we know the reaction can go either way. So you have to make sure you write the reaction as it's supposed to be written. And if it's written one way where it's exothermic, if you turn it around, it's going to be endothermic. So make sure you write it correctly. That does matter. But if a reaction is written to be endothermic, that means that the reaction requires heat to occur. It has to take heat in from the surroundings. that allows us to treat heat as a reactant. And we said previously, if we add a reactant to equilibrium, it's going to shift the reaction to the right. So an endothermic reaction, heat is considered to be a reactant. If we increase the amount of heat, which usually that's measured through temperature. If I raise the temperature, that's like adding heat. The reaction for endothermic will shift to the right. On the other hand, if it's exothermic, that means heat is being produced by the reaction, so heat's a product. If I raise the temperature, I'm increasing the amount of a product, so that's going to shift the reaction back to the left. Okay? So, I have a reaction given. Cobalt water complex reacts with 4 chloride ions to form cobalt chloride complex plus 6 waters. The reaction has a positive delta H. If delta H is positive, that means it's endothermic, which means I can consider heat to be a reactant. So I'm just going to throw heat over on the reactant side. And now, if I heat it up, if I add heat, if I raise the temperature, the reaction should shift to the right. So what I notice is that at room temperature, the solution's kind of purple. If I heat it up, which the purple is a mixture of the pink and the blue, if I heat it up, it's going to shift it toward the right. The complex on the right is more blue, and what I notice is my purple color here turns into more of a deep blue color over here. When I heat up the reaction, it shifts toward the right, making the solution become more blue. On the other hand, if I add ice and cool it down, that's going to, if I remove heat by lowering the temperature, then heat is being removed. It's going to pull the reaction to the left, turning it more toward the pink form, and I can see that in my test tube. The reaction vessel becomes pink. All right, so we have the production of ammonia. When I look at the production of ammonia, it is an exothermic reaction, so heat is a product. I notice that Kc for this reaction is 0.1. Now, if I am a company that makes ammonia, that's really bad. That means that whenever I put nitrogen, hydrogen into the container and try to get the ammonia to form, only about 10% of the reactant molecules are going to actually turn into products. 90% or 91% are going to actually stay in the form of the reactants. If my company is trying to make money by making ammonia, that's going to make it a much more difficult job. So, somehow, scientists or chemists are able to do this reaction effectively because in the world, 200 million tons of ammonia are produced every year. It's one of the most important compounds that in various types of plastic being made, petroleum products, just all kinds of pharmaceuticals. Ammonia is an important reactant in a lot of those processes. So we need a lot of ammonia. We have to find a way to make this reaction work, even though the K value is extremely low. So how do we do it? Well, we have to manipulate the equilibrium the best we can. Essentially, we're using LeChâtelier's principle to say, okay, well, first of all, if I want to shift the reaction to the right, the first thing I could do is add more reactants. The more reactants I pump into the container, the more it's going to shift it to the right and make more ammonia. So when we perform this reaction in an industrial setting, we pump in high pressure nitrogen and hydrogen. We put the pressure of both gases at like 200 bars, which a bar is like pretty close to equal to an atmosphere. So 200 atmospheres of pressure are pumped into the container of reactants. As the reaction forms ammonia, we're going to constantly remove the ammonia from the container the best we can. Now, if we cool it down, ammonia will actually turn into a liquid, and then we can drain the liquid out of the container. Now, we do cool it down to get the ammonia out, but there's another reason. Since the reaction's exothermic, when we remove heat, that's another factor that's going to shift the equilibrium to the right and increase the amount of ammonia that's formed. So by lowering the temperature, it allows me to remove the ammonia because it puts it as a liquid, and it shifts it to the right because of the heat being a product of the reaction. Now we do have an issue though. This reaction has a high activation energy, and when we cool it down, that's also going to slow the reaction down. I don't want a reaction that's going to take a week or a month or a year to reach equilibrium, which a slow reaction that has a high activation energy takes a really long time to get to its equilibrium point. Okay, so what we have to do, if we need to do it at low temperatures, but we also need the reaction to be fast, we have to find a catalyst. Okay, and they do have a catalyst that helps this reaction occur. Even at low temperatures, we can find a catalytic pathway or a mechanism to get the hydrogen and nitrogen to turn into ammonia with smaller activation energies so the reaction goes faster. Okay, now, bringing a catalyst into the idea of it, we learned in chapter 14 that catalysts will speed up a reaction by changing the way we get from reactants to products. Okay, but it doesn't actually change what the reactants are or what the products are. So when we add a catalyst, it helps us get to equilibrium faster, but it doesn't change what equilibrium is. Remember, the equilibrium constant is a ratio of products to reactants. When we add a catalyst, it won't change the final ratio of products to reactants we're going to get. It doesn't help me get more products. It just helps me get to equilibrium faster. Once I get there, then when we start applying LeChâtelier's principle and trying to manipulate the equilibrium, every time we do a manipulation, the catalyst is going to help it reset itself quicker every time. So basically, we can more efficiently use all the things on the previous slide that we're controlling. We can use all those more efficiently since the catalyst is going to help us get there quicker. Okay? Now, it's demonstrated right here. The black line shows the rate that the reaction would kind of get to equilibrium, which about right here is where it gets to equilibrium, naturally. Okay? And notice it's kind of a steady reaction. It eventually gets there, but it takes about this much time to get to equilibrium. If we add a catalyst, that's the green line now, the reaction with the catalyst, the initial reaction is going to go faster. I'm going to get to my proper ratio of ammonia to nitrogen and hydrogen a lot faster. I get to my equilibrium in this example in about half the time that it did when it wasn't catalyzed. So a catalyst is going to get me to the same ratio faster. All right, now a key there. The catalyst is not going to change the equilibrium constant. Even when all the other things that we've been talking about, where I add a reactant or add a product or heat it up, or well, actually, if I add a reactant, add a product, increase the pressure or shrink the volume, none of those things are going to change the equilibrium constant. Okay? All those things that I just said, what they do is they change one of the numbers in the ratio so that it doesn't, if the ratio of products to reactants doesn't equal the equilibrium constant, if something we do messes up that ratio, the reaction is going to try to get back to the ratio. It doesn't actually change what the ideal ratio is, though. K stays the same. Okay? The only thing that will change the value of K is if we change the temperature. If you remember, the equilibrium constant came from the rate constants. The rate constant of the forward reaction, the rate constant of the reverse reaction. When we manipulated the equation, we ended up with, I think it was Kf over Kr, K forward, K reverse. If we change the temperature, the rate constants change. If the rate constants change, then the equilibrium constant changes too. Okay? So the only thing that will change the equilibrium constant for a reaction is changing the temperature. All right, we already talked about all that. So now the next few slides are just a few practice problems. If I get a chance to, I'll come back and make another video for this one. It'll be the next one in YouTube. For now, though, I've covered all the content for Chapter 15. Again, the next video will just be practice problems. I'll get it up when I can.